This is the second of 3 videos on the idea of limit. I am not presenting the formal definition yet. I am trying to explain the intuition behind what it means for a function to have a limit using geometry and algebra. In the first video, I presented 2 examples of functions that had a limit. In this one, I will present 2 more examples of limits that do not exist. As a reminder, when I say that limit as x approaches a of f of x equals L, what I roughly mean is that if x is close to a but not a, then f of x is close to L. And again, this is not a formal definition, we'll make this rigorous later. This is what I concluded in the first video that you should watch before this one. I'll put a link in the description. Let's try to use the same ideas in a couple of new cases. First, my example number 3 is going to be this function h, defined by the equation h of x equals sine of pi over 2x. h of 0 is undefined, I cannot plug x equals 0. Perhaps it is undefined like my first 2 examples, but the graph of the function has simply a hole in it, and the function has a limit. Let's find out. This function is harder to manipulate algebraically than the first 2. So instead, I'm going to look at a table of values. I'm going to try to evaluate this function when x equals 1, 1/2, 1/3, and so on. I've prepared these numbers so they will be easy to evaluate because the argument of sine is going to come up to be a multiple of pi over 2. Remember that sine is in radians. At this moment, I invite you to pause the video, compute these values, you should see a pattern, and then continue watching. This is what I got. H of 1 is 1, h of 1/2 is 0, h of 1/3 is -1, and then it goes back to 0, and to 1, to 0, to -1, and so on. And in fact, as I make x closer and closer to 0, this function keeps oscillating between -1 and 1. And before x reaches 0, it will go up to 1 and down to -1 infinitely many times, because it keeps oscillating faster and faster. This happens both for positive numbers and for negative numbers. So in this case, if x is close to 0, then h of x is not close to one single number, because it's all over the place between -1 and 1. And we're going to say that the limit as x approaches 0 of h of x does not exist, often abbreviated DNE. Because for a limit to exist, the function must be approaching one single number. There are many other examples of limits that do not exist. And there are some examples of limits that do not exist in a very specific way that deserves a name of its own. This is going to be example 4. I'm going to look at the function f defined by the equation f of x equals 1 over x minus 1 squared. In this case, f of 1 is undefined. And I assume you know what the graph of this function looks like. It has a vertical asymptote, like this. Because when x is very close to 1, but not 1, x minus 1 squared is going to be very close to 0 but positive. And 1 divided by a number that is very close to 0 but positive is going to be very large. In fact, arbitrarily large. This function gets as large as we want. When this happens, we're going to say that the limit as x approaches 1 of f of x is infinity. But we are also going to say that the limit does not exist. And I know, this seems contradictory. This seems like bad notation. Perhaps it is. But it is standard and is a notation that all calculus textbooks use, so I'm going to use it as well. The limit does not exist because in order for the limit to exist, when x is close to 1 but not 1, f of x should be approaching one single number. And that's not happening. F of x is not approaching any one single number. Infinity doesn't count, infinity is not a number, because it's getting arbitrarily large. So, when we say the limit is infinity, we are saying 2 things. First, that the limit does not exist, f of x is not approaching any one single number, and 2, that the limit does not exist in this very specific way. F of x is not approaching any one single number because it's getting arbitrarily large. There is a second family of examples where the limit does not exist also for a different, very specific reason. That's going to be example 5 in the next video, where I will also talk about side limits.